Number 6 is a question on the Cope rearrangement, which you learned for the third exam. Now, how do we know it's a Cope rearrangement? Well, one, the question asks, what is the product of the following Cope rearrangement? But also, what if they didn't say that? Well, I see only heat over the arrow, which usually is typical of a rearrangement. And I also see a carbon chain with a bunch of double bonds in it. So that's your next hint. It's probably one of those rearrangements. The final way to make sure of that is start from the end of one double bond and number to the end of the other. So I have 1, 2, 3, 4, 5, and 6. And whenever you do a rearrangement, there should be a 6 carbon chain where the double bonds exist between 1 and 2 and 5 and 6. So this is definitely a rearrangement, even if they didn't tell you it was. So they didn't have to tell you it was in the question, and you would still have to be expected to know. So now what do you do during this rearrangement? Well, kind of like the Diels-Alder reaction, there are 3 cyclic arrows you have to draw. Each one starts from the center of a bond and ends at the center of a bond. So start from a double bond. Let's say the bond between 1 and 2. The arrow will start from that double bond and move down to the single bond between 2 and 3. Then you start from the next bond over, the bond between 3 and 4, and you draw that going to the bond between 4 and 5. Finally, you start from the bond between 5 and 6, and you go to the bond between 6 and 1. But there isn't any bond between 6 and 1. So what this means is you're now forming a bond between 6 and 1. Now let's follow those arrows and figure out what that's supposed to look like. So the way you can do this is just redraw everything exactly the same as you started with, but make sure you draw it in pencil so you can erase things. Let's start with this first arrow. The arrow starts from a double bond, which means that double bond is becoming a single bond. You're using up electrons from it. That arrow ends at the bond between 2 and 3. So I'm making a double bond there. The next arrow starts from a single bond. If you have an arrow starting from a single bond, you're breaking that bond. So the bond between 3 and 4 is now gone. But those electrons were used and went to the bond between 4 and 5. Since that's going to where there was a single bond, that means you're now making a double bond between 4 and 5. Finally, your arrow starts from the double bond of 5 and 6, which means you are erasing one of those 2 bonds. You're making it a single bond now, and those electrons are going to the 0 bond, the no bond, between 6 and 1, which means that is now going to be a single bond. So this is possibly your answer, and I'm pretty sure it was an answer choice. Yes, I think. Actually, good. They were kind of nice to you in the fact that they never gave you this as an actual answer choice on the answer key. There's no answer where there's just an OH on a carbon-carbon double bond. So this tripped a lot of people up when they took this question. This is what I got, and I did everything right. Why isn't this an answer choice? Because you have to remember one really, really, really important rule. Whenever you form at the end of a reaction either O- on a carbon-carbon double bond or OH on a carbon-carbon double bond like what we did, these always tautomerize back into their ketone form or their carbonyl form. The electrons of the oxygen swing down and this goes out and grabs a proton. The electrons of this oxygen swing down and this goes out and grabs a proton, and that OH gets deprotonated. Either way, you end up with a double bond O, and that's what they expected you to know for this question as well. Which means the final answer of this was actually choice B, because what you get is 1, 2, 3, 4, 5, 6. This double bond isn't anywhere near an OH, so it stays the same. But this double bond is now gone, and there should be a double bond O on it, because they're tautomerized. Okay, so what happens is this swings down, this goes out and grabs the proton. It doesn't have to necessarily be this one, but it's grabbing some proton and this OH is getting deprotonated somehow. But you end up with a double bond O there, and that gives you choice B based on how they drew it. I drew mine a little weird, but if you count along, you can see that going one way, you go 1, 2, 3, 4, 5, the double bond starts 5 away from the carbonyl. And if you look at choice B, that is also true if you count in the clockwise direction, 1, 2, 3, 4, 5. Okay? So that's how you do number 6.